Hi, my name is Heini Väisänen and I'm a lecturer in social statistics and demography at the University of Southampton. Today I will talk to you about multinomial logistic regression, which is a regression model that you can use when you have categorical response variables. This first part is an introduction to the method, just looking at when you might use the method, how it works, and then giving you a simple example of how to interpret results from the model. So the outline of the session is as follows. We will first start by talking about categorical response variables. So what kind of outcome variables you might use with this type of regression models. Then we will move on to talking about how the model actually works. And then we will look at an example where we study economic activity and its relationship with gender using these methods. And if you haven't yet watched binary logistic regression videos, I would recommend you watch them first before you move on to these sessions. So what do we mean by categorical response variables? Often we're interested in variables that have more than two categories, so 3 or higher, and they are not ordered. So the categories that we use, we couldn't say which category is larger than the other, but we can clearly say to which category all of our respondents or all of our cases in our data set belong to. So examples of these type of outcomes are, for instance, voting intention. So we might have data about what party respondents are planning to vote in the next election, whether it's Conservative, Labour, Liberal Democrats or some other party. In this case we would have 4 categories. It could be if you're a demographer like me and interested in delightful subjects such as cause of death. So we might be interested in figuring out which characteristics are associated with different types of cancer as cause of death, for instance. The idea behind multinomial regression models is that it's basically an extension of the binary logistic regression model. And that's why I recommend that you watch those videos first before you move on to this one. So instead of just running one model, like we do in the binary logistic regression model, we model as many pairs of categories, response categories as we need. If our outcome variable has R number of categories, then there are R times R minus 1 possible pairwise models that we could run. But luckily we don't have to run as many models. Actually we only need R minus 1 of these models. So if we have 3 categories in our outcome, so for instance if we were interested in whether someone is going to vote for Conservatives, Labour or some other party, we would have 6 different possibilities of pairing them up. So we could pair categories 1 and 2, 1 and 3, 2 and 3, or 2 and 1, 3 and 1, and 3 and 2. But actually 1 and 2 is the same pair as 2 and 1, etc. So half of these drop out already, and actually we will end up only modeling 2 pairs because we will select one of the categories as baseline or reference category and only compare the other 2 outcomes to that category. And I will walk you through what that means. So, the interpretation of a multinomial regression model is based on this idea that you have a baseline category, or it's also called reference category, of the outcome. So if you've used regression models before, you might be familiar with using dummy variables as explanatory variables. And if you do that, you choose one category as a reference category, and then you compare the other categories to that reference. And it's basically the same idea here, except that you're doing that for the outcome. You might as well do it for your explanatory variables, but let's not talk about that yet. So the interpretation of this model depends basically on which response corresponds to the numerator and which does correspond to the denominator. The category corresponding to the denominator is called the reference or the baseline category, and we compare the numerator to that category. Mathematically speaking, it doesn't really matter which baseline category you choose, but it usually is easy. There are different choices that you can make which might make your life easier when you're trying to interpret the results of the model. So in case your outcome category is ordered, you might choose the first or the last category. I know I said earlier that normally we would use nominal variables as outcomes here, but sometimes we might have ordered variables and we might use multinomial regression to model those. It could be the most meaningful category in your outcome depending on your research question. It could be the most frequent category, so you just look at which category has the most responses and then you compare everybody else with that. And the only rule that I have against choosing a category is that it's usually not a good idea to choose a rare category as the reference category, because that can lead to inflated odds ratios and difficulties in interpretation of the model. Once you have chosen your baseline category, you can then run your models. So staying with our example of a model where we have 3 categories of the outcome, you could, for instance, choose one of them as the reference category, and you would then end up with 2 model equations. So these are like 2 binary logistic regression models, but they are run at the same time, and you compare 2 of the categories to the third one, which is the reference category. So looking at these equations here on the slide, which outcome category 1 to 3 do you think is the reference category here? Remember earlier that I talked about numerators and denominators and their relationship to the reference category. And as you can see, the denominator in both of these equations is category 3. So that means that in whatever our outcome is here, the one that we coded as outcome number 3 is the reference category, and then we compare categories 1 and 2 to that in our models. Next, I will move on to looking at an example which makes it a bit easier to understand what exactly is going on here. So our example looks at the association between gender and economic activity. Our outcome variable has 3 categories. So whether someone is economically inactive, so maybe they're on parental leave, or maybe they're retired, whether they are unemployed and looking for work, or whether they are currently in employment. And then we're looking at how whether you're a man or a woman is associated with your likelihood to be in these different categories. Here's our data. These are real data coming from ONS Opinion Survey Wellbeing Module collected in April 2011, and the data source is shown here on the slide. And using these data, our outcome variable is distributed so that the most common category is in employment. So about 56% of our respondents were working at the time of the survey. The second most frequent category was economically inactive. So around 39% of our respondents were not working and not looking for work. So maybe they were retired, on parental leave, or students, or something like that. And about just under 5% of the respondents were unemployed at the time of the survey. Overall, we have 1,124 respondents here in our data set. Out of these respondents, around 54% were women and around 46% were men. So when we put economic activity as the outcome in our multinomial regression model, we will end up with 2 equations as shown here and as seen on the previous slide. So one is comparing category 1, so economically inactive, to category 3, in employment, and the second equation is comparing category 2, which is unemployed, to category 3, which is in employment. And we have chosen here category 3 in employment as the baseline category because it was the most frequent category in our data set. Looking at the equations, B/1 in the first equation is the effect of our explanatory variable, so gender, on the log odds of being in category 1 instead of category 3, so being economically inactive rather than in employment. And B/2 is the effect of gender on the log odds of being in category 2, so that is unemployed, instead of category 3, which is in employment. And like in binary logistic regression, we can obtain odds ratios by calculating the exponentiated values of B/1 and B/2 and then use that to interpret our results. I've used data here to run these models. You might use some other software, but the results are likely to look quite similar to here. So here the results are shown as on the logit scale. So you might remember from binary logistic regression that this is a scale that we don't often use to interpret the results because it's not very intuitive, but it shows you already some information about what the relationships are going to look like. So if we look at the first set of results here, our first equation, which is comparing being unemployed to being in employment, we have one explanatory variable, which is gender. Man is the reference category and woman is the category that we see here. And we see that there is a negative effect for being woman and being unemployed. So that means that women are less likely to be unemployed rather than in employment when we compare women to men. So as you can see, these models become quite complicated quite soon because you are comparing so many different sets of variables. So you have the reference category of the outcome variable, and since we have a dummy variable as our explanatory variable here, we are also comparing men and women. The second equation shows that this time the coefficient is positive, so it means that women are more likely than men to be economically inactive rather than in employment. Usually, if we want to say something a bit more meaningful about our results, we might want to look at the results in the odds scale. And this is how these results look like in Stata. So it's exactly the same model, it's just that I've asked Stata to show the results on the odds scale rather than as log odds. And here you can see that for women we have an odds ratio which is below 1, which means that there is a negative association, like we already saw from the log odds. And for the second equation, the odds ratios are larger than 1, which means that there is a positive association. If we wanted to put these results into English language, we might want to say something like this. If we were to interpret these results using the odds scale, we could say that the odds of being economically inactive rather than in employment are 73% higher for women than for men. And below you can see how I came up with this number 73%. And for the second equation, we could say that the odds of being economically inactive rather than in employment are 42% lower for women than for men. Sometimes, instead of using odds to interpret your results, you might want to use predicted probabilities. Most statistical software will calculate these for you, but I'm going to show how to do this by hand so that you know where these predicted probabilities are coming from. So if you remember how predicted probabilities are calculated for binary logistic regression, you'll see that this is quite similar. The only difference is that since we are dealing with two pairs of equations, we also need to calculate a higher number of probabilities using more equations than we do in a binary logistic regression model. So basically what we do, if we want to know what is the probability of someone of being in category 1, so in our case this would be economically inactive, we would take the first equation, so the equation corresponding to the category economically inactive, exponentiate that, divide that by 1 plus the exponentiated value of the first equation plus the exponentiated value of the second equation, which in our case is the equation for unemployment. If we want to calculate the predicted probability for category 2, it's otherwise the same thing, so the denominator is exactly the same as before, but the numerator changes, so now in the numerator we plug in values from the second equation, which is the one for unemployment. For the reference category, the numerator is just 1, that's always the case for the reference category, and the denominator is still the same as it was for the other two categories. And if you had more than 3 categories in your outcome, then your equations would be even longer than they are now, because in the denominator you would always have to have all of your equations shown. I've shown here how you can calculate the probabilities for women, and I've plugged in the values from the table that I showed you earlier, the one that showed the results in the log-odds scale. And we would always use the log-odds scale here and then exponentiate that. So the first equation calculates the probability of being economically inactive if you're a woman. The second one calculates the probability of being unemployed if you're a woman. And the third one calculates the probability of being in employment if you're a woman. And the difference between calculating the probabilities for men and for women is that for women we need to take into account beta 1 and beta 2, so the coefficients attached to the gender explanatory variable, which in the first equation is 0.550, and in the second equation is negative 0.537. For men, we can drop these because they are the reference category in this dummy variable, so the coefficients would be multiplied by 0, and when you multiply something by 0, it disappears. So for men, we would only need to exponentiate the constants from these two equations. And if we calculate these probabilities for men as well, we could then summarize our results, for instance, using these two sentences. Among women, the probability of being economically inactive was 46%, in employment 51%, and unemployed 3%. Among men, the probability of being economically inactive was 32%, in employment 61%, and unemployed 7%. Well, for multinomial regression models, predicted probabilities are usually quite useful to use for interpretation, because like you saw with the odds example, it can get quite complicated with the multiple comparisons otherwise. Thank you.